Hello and welcome to Fluid Mechanics. My name is Dr. Mark Taylor, lecturer in Civil Engineering. So this is Unit 3, Fluid Statics. So in this unit we're going to look at the subject of pressure, how we measure pressure, forces, head, and introduce the subject of hydraulic structures and the forces that may be acting upon them. So during this session, I aim to establish the variation of pressure in a fluid at rest, explain the use of manometers to measure pressure, calculate forces on plane and curved surfaces, consider the forces of buoyancy, and determine the stability of submerged and floating objects. At the end of this lesson, you should be able to explain the concept of pressure, define the units of pressure measurement, describe methods of pressure measurement, identify applications for pressure measurement devices, explain the derivation of forces acting on submerged structures, understand the forces acting on a cylindrical pressure vessel, and define buoyancy and explain how a ship remains stable. Fluid statics is concerned with the balance of forces in fluids at rest. Fluid statics is a study of fluids in which there is no relative motion between the fluid particles. No relative motion, then no shearing stress, since velocity gradients are required for shearing stresses to be present. The only stress that exists is a normal stress, the pressure. So it is the pressure that is of primary importance. Let's now focus on the subject of pressure. So here's a question that you should be able to answer by the end of this lecture. What would the external hull pressure per square metre be on a submarine at a depth of 150 metres in seawater? Blaise Pascal was a French mathematician, physicist and philosopher. He was a highly gifted scientist at a young age, and he invented an arithmetic computer at the age of 19 called La Pascaline, shown below. He discovered the principle of fluid mechanics that carries his name. Many units had appeared as the units of pressure measurement, but it was decided to use the Pascal in SI units in memory of his great achievements. The term pressure is used to describe the force exerted by water or a liquid on each square metre of some object submerged in the water or the liquid. That is the force per unit area. It may be at the bottom of a tank, the side of a dam, a ship, or a submerged submarine, and it's calculated as follows: pressure equals force over area. Sometimes pressure is measured in pascals, in recognition of Blaise Pascal, who clarified the modern day thinking on pressure and barometers for measuring atmospheric pressure. A common unit is bars, so 1 bar is equal to about 10 to the power of 5 pascals. 1 pascal is a very small quantity of pressure, so kilopascals are often used. A conversion table for pressure units is given below. In some cases, atmospheric pressure can be used. 1 atmosphere is equal to 101,325 pascals. 1 atmosphere is the standard 1 atmospheric pressure in meteorology and is called standard atmospheric pressure. There are 2 methods used to express pressure. The first one is based on the perfect vacuum, and the second based on atmospheric pressure. In relation to a perfect vacuum, this is known as absolute pressure. In relation to atmospheric pressure, this is known as gauge pressure. And the gauge pressure is equal to the absolute pressure minus the atmospheric pressure. Pressure has 3 characteristics. The pressure of a fluid always acts perpendicular to the wall in contact with the fluid. The values of pressure acting on any point in a fluid at rest are equal regardless of the acting direction. And finally, the fluid pressure applied to a fluid in a closed vessel is transmitted to all parts at the same pressure value as that applied, and this is known as Pascal's law. The values of pressure acting on any point in a fluid at rest are equal regardless of its acting direction. Consider the triangular prism of unit width in a fluid at rest as shown. The pressure acting on the small surfaces delta A1, delta A2, and delta A equals P, P1 and P2. The following equations are obtained from the balance of forces in the horizontal and vertical directions. Note that the weight of the triangular pillar is omitted as it is considered infinitesimal. Therefore, we end up with the following relationship. Pressure 1 equals pressure 2 equals the pressure P. So because the angle theta can be given any value, values of the pressure acting at one point in a fluid at rest are equal regardless of its direction. The fluid pressure applied to a fluid in a closed vessel is transmitted to all parts at the same pressure value as that applied, and this is what's known as Pascal's law. So let's consider a hydraulic press. When the small piston of area A1 is acted upon by the force F1, the liquid pressure is equal to the F1 over A1. To find out the force F2, we multiply this pressure by area 2. The force F2 is equal to F1 multiplied by A2 over A1. So this device can create a large output force from a small input force, and this is how a hydraulic press works. However, we're not getting something for free here. The smaller piston has to travel quite a large distance to allow this to happen, and there'll also be some heat losses too. So in a fluid at rest, the pressure varies according to the depth. Let's consider a column of fluid as shown on the right. We're going to assume that the section area is delta A, and the pressure acting upwards on the bottom surface is P. The pressure acting downward on the upper surface, delta Z above the bottom surface, is P plus delta P over delta Z, which is the change in pressure with respect to the change in depth, multiplied by delta Z, the change in depth. Then from the balance of forces acting on the column, the following equation is obtained. And we find that these forces balance, i.e. they equal zero. So the change in pressure with respect to the change in depth can be written as delta P over delta Z, the change in pressure with respect to the change in depth, is equal to minus rho g. And because the density rho of a liquid is constant, the following equation ensues. So the pressure is minus rho multiplied by gravity multiplied by the integral of delta Z, which equals minus rho g Z plus a constant. So if we now consider the figure opposite, where the base point is set at Z0, below the upper surface of the liquid as shown. P0 is the pressure acting on the surface, and this would be atmospheric pressure. So then P equals P naught when Z equals Z naught. So C, the constant from the previous equation, is P naught plus rho g Z naught. And if we substitute this into the previous equation on the slide before, we then get pressure equals P naught atmospheric pressure plus rho g h, the depth to the point that we're measuring the pressure. Thus it's found that the pressure increases in proportion to the depth. And we end up with the equation pressure equals P naught, which would be the atmospheric pressure on the surface, plus rho gh. So let's now look at some pressure measurement devices. The device that measures the fluid pressure by the height of the liquid is called a manometer. Consider measuring the pressure of a liquid flowing in a pipe. The pressure P can be obtained by measuring the height of the liquid H coming upward into the manometer made to stand upright. When P naught is atmospheric pressure and rho is the density of the liquid, the following equation is obtained. The pressure equals P naught atmospheric pressure plus rho gh. When the pressure in the pipe is too large, using a piezometer becomes an issue, as the value of H has to be really large. So an alternative is to use a U-tube manometer with a manometer fluid which is more dense, typically mercury. So here we can see below how you can now calculate the value of P, considering P0 atmospheric pressure, rho dash, the density of the mercury, times gravity, times the height of the mercury, h dash, minus rho, the density of the liquid we're measuring, times gravity, times h. An elastic type pressure gauge measures the pressure by balancing the pressure of the liquid with the force of deformation of an elastic solid. The Bourdon tube was invented by Eugene Bourdon, who was born in 1808 and died in 1884. The Bourdon and diaphragm gauges are widely employed for this type of pressure gauge. The Bourdon gauge is the most common type used in industrial settings. The Bourdon tube is a curved metallic tube of elliptical cross-section and is closed at one end, which is free to move, but the other is fixed to a frame. When the liquid under pressure enters the tube from the fixed end, the cross-section tends to become circular, so the free end moves outwards. When the pressure becomes less than the atmospheric pressure, vacuum, the free end moves inward, so the gauge can be used as a vacuum gauge. A diaphragm Bourdon pressure gauge is constructed with a diaphragm which isolates the Bourdon tube from the measuring fluid. In this case, the Bourdon tube contains a fluid which transmits pressure from the measuring fluid. Such a gauge can be used to measure the pressure of a corrosive fluid or a very high viscosity fluid which might corrode or solidify in the Bourdon tube. Electric pressure transducers convert the force or displacement passing through the diaphragm using a strain gauge, and they convert this into electrical voltage. An amplifier circuit can then be used to increase the gain of the output for recording or data acquisition purposes. These types of pressure gauges are useful for measuring fluctuating pressures. In the strain gauge type, there are resistive metal foils which are bonded to the metal diaphragm. So let's now look at pressure forces on submerged surfaces. So let's now consider water pressure acting on a dam. And here we can see a cross-section through the dam. So if we now consider the total force caused by the water pressure acting on the bank, shown at an angle theta to the water's surface, if we disregard the atmospheric pressure, the total pressure, delta P, acting on a minute area, delta A, is rho gh delta A equals rho gy sine theta delta A. So the total pressure, capital P, acting on the underwater area of the bank wall is equal to the integral of delta P, which is equal to rho g sine theta and the integral of y delta A. When the centroid of the bank wall is g, its y coordinate is yg, and its depth g is hg. So therefore the following equation is obtained. The pressure is equal to rho g, the height hg, times the area. So the total force P equals a product of the pressure at the centroid G and the underwater area of the bank wall. So let's now consider the water pressure acting on a sluice gate. We'll see from this diagram that the axis of rotation of the gate is just on the top water level, shown here with a red arrow. So if we now consider a rectangular sluice gate, the force P acting on the whole plane of the gate is P equals rho g y subscript g times delta A. The force acting on a minute area delta A, a horizontal strip of the gate face, is equal to rho g y delta A. The moment of this force around the x-axis is rho g y delta A y, and the total moment on the gate is rho g times the integral of y squared times delta A. The integral of y squared delta A is the geometrical moment of inertia Ix for the x-axis. So now let's locate the action point P, at which a single force P produces a moment equal to the total sum of the moments around the turning axis of the sluice gate. When the location of C is y subscript C, Py subscript C equals rho g Ix, where Ig is the geometrical moment of inertia of area for the x-axis. Substituting, yc equals yg plus ig over ayg equals yg plus h squared over 12yg. It's clear that the action point C of the total pressure force P is located deeper than the centroid G by h squared over 12yg. So now we're going to look at a different example where the gate is now located under the water, and you'll see now that the pivot point is located a distance h1 down from the surface of the water. So in this case the sluice gate is now located under the water, so the position of yc in such a case where the sluice gate is located under the water surface is shown in the figure. Hg is then substituted for yg in the second term on the right using yc equals yg plus h squared over 12hg. So let's now consider the pressure forces on a cylinder. So the figure here shows the pressure distribution on the inner cross-section of a thin cylinder, and B, the pressure distribution on the longitudinally half-section thin cylinder. So consider the case of a thin cylinder, in this case a can of iron brew, where the inside pressure of the liquid is acting outward, as shown in the figure. So what kind of force is required to tear this cylinder apart in the longitudinal direction, B? Consider the cylinder longitudinally half-sectioned, as shown in B, with a diameter d, a length L, and an inside pressure P. The force acting on the assumed vertical centre wall ABCD is PdL, which balances a force in the x direction acting outward on the cylinder wall. The force generated by the pressure in the x direction on a curved surface equals the pressure PdL, because the same pressure acts on the projected area of the curved surface. So the force generated by the pressure in the x direction on a curved surface equals the pressure PdL, because the same pressure acts on the projected area of the curved surface. This force is the force 2TL. T is the force acting per unit length of wall, which tears the cylinder longitudinally in half along the line BC and AD. 2TL equals PdL, or T equals P multiplied by D over 2. If the tensile stress caused by T is lower than the allowable stress, the safety of the iron brew is assured, i.e. the can will not burst. By utilising this principle, a thick-walled pressure tank can be designed. Now, go and drink some iron brew. So finally, we're going to have a look at buoyancy and ship stability. So Archimedes discovered that the fluid pressure acts all over the wetted surface of a body floating in a fluid, and the resultant pressure acts in a vertical upward direction. The buoyancy of air is small compared to the gravitational force of the immersed body, so it's normally ignored. Consider a cube placed in a liquid of known density ρ. The pressure acting on the cube, because of the fluid in the horizontal direction, is balanced left and right. In the vertical direction, where atmospheric pressure is P0, the force F1 acting on the upper surface A is expressed by P0 plus rho gh1 multiplied by A. The force F2 acting on the lower surface, F2, is P0 plus rho gh2 multiplied by A. When the volume of the body in the liquid is V, the resultant for F from the pressure acting on the whole surface of the body is F2 minus F1, which leaves us with rho gV. The same applies to the case where the cube is floating as shown. The body of the liquid experiences a buoyancy equal to the weight of the liquid, displaced by the body. This result is known as Archimedes Principle. The centre of gravity of the displaced liquid is called the centre of buoyancy, and is the point of action of the buoyancy force. The ship shown below has a weight, W, and is inclined by a small angle θ due to the waves. The location of the centroid G does not change with inclination of the ship. However, the centre of buoyancy, C, moves to a new position, C'. A couple of forces is produced, and this couple restores the ship's position to one of stability, i.e. floating upright. The forces of the couple, Ws, are called restoring forces. The intersecting point M on the vertical line passing through the centre of buoyancy, C', and the centre line of the ship is called the metacentre, and the line GM is called the metacentric height. If M is located higher than G, the restoring force acts to stabilise the ship. If M is located lower than G, the couple of forces acts to increase the roll, and this makes the ship unstable. So in summary, pressure is equal to the force divided by the area of application. The pressure increases in proportion to the depth. Pressure is measured in pascals. Pressure measurement devices include Bourdon gauges and manometers. Mercury is often used in U-tube manometers to measure high pressures. We considered the forces acting on a dam and on a submerged sluice gate, and we'll look into these in more detail in the practical tutorial questions. Fluid pressure acts all over the wetted surface of a body floating in a fluid, and the resultant pressure acts in a vertical upward direction. The intersecting point M on the vertical line passing through the centre of buoyancy, C', and the centre line of a ship is called the metacentre. So after we've finished the tutorial questions for Unit 3, we'll move on to the fundamentals of flow, and then we'll look at discharge, continuity, energy, and momentum. Thanks for listening. Bye for now.